events, I will try to make up for the lost time by going quickly over this material about enumeration algorithms, various circuits, and their use in query evaluation. I'm Antoine Amarili from Telecom Paris, by the way. So let me give you a brief introduction to why we want to do this, intended mostly for database people and database theory people. This talk is about the approach of intentional query evaluation, where we have a query, we have a database, and instead of evaluating the query directly on the database, we will compile the query on the database to some circuit in a tractable class of circuits, like those with the weird names, d-DNNFs, UOBDDs, and so on. This is also called grounding the query on the data. It's related to computing the provenance of the query on the data. And then we will use this circuit to retrieve the answer that we were interested in originally. We have seen on Monday, with two great talks by Dan and Michael, how to use the intentional query evaluation approach for tasks like counting, weighted counting, and probability computation. Today, or at least this morning for my talk, we're going to use this intentional approach for something else, for enumeration of query answers, okay? So I will cover some preliminaries and state the problem a bit more formally. And then most of my talk will be spent on the question of efficient enumeration for circuits in a specific class, so d-DNNF set circuits. Indeed, unlike weighted counting or probability computation, it's not so clear how do you even define enumeration with circuits and how do you get efficient enumeration results for circuits. So this is what I'll be presenting to you. And then I will tell you how these results for enumeration on circuits can be used for query evaluation and other such applications. Okay. So this is joint work with a bunch of people, some of which are in the room, some of which have been present during the Simon's program. So Pierre Boris, Florent Capelli, who is here, Louis Jochier, Stéphane Mengel, Michael is here also, Martin, Mathias, and Christian. And it's been done in a series of papers. So we started at ICALP 2017, this approach with the result on circuits and its application to monadic second-order query evaluation. Then we've mostly focused on monadic second-order queries on trees under updates, that I will talk more about, and monadic second-order queries on words in the framework of document spanners, which I will also talk about. And more recently, we've been extending this to weirder queries like annotated grammars on text. And very recently, a few weeks ago, ranked enumeration for monadic second-order queries. Okay, so what's nice about giving these kind of talks at the Simon's Institute program is that at least for those of us who've been here since the beginning of the program, yes? Oops. Right. So yeah, I will reveal that this has been covered in Nofar Karmeli's talks at the September workshop. So enumeration algorithms are a way to measure the complexity of tasks where it's not just a decision problem like yes or no, but the problem is to compute an answer set which is very large, and so you need to change a bit the complexity measure because just writing down the answer, writing down the output takes up so much time. So we do this by splitting the computation into two phases. So given the input, say a database, and we want to compute some query results, we have a first phase, what's called the pre-processing phase or the indexing phase, that ideally runs in linear time in the input. Not always possible, but this is the best we can hope for. And computes from the data some representation that makes it easier to compute the query answers, the indexed input, or so you can think of this as a compressed version of the answers to produce, or a factorized representation of the answers, or some pre-indexed version of the database, whatever. And then you have a second phase, the enumeration phase, that takes this and must produce all of the results we're interested in without duplicates as efficiently as possible. And here, efficiently would mean each result is produced in linear time in the size of this result. So if the results to produce have constant size, we would want each result to be produced in constant time, independent from the size of the database. So, I mean, probably most of you have seen this stuff before, but if you have not, this is a rather strong guarantee. Like if you want to compute a query where the answers have size 4, like some constant, I give you a database and you have a delay that it is a constant that depends on 4, but like 4 is a constant also. So there is a certain number of operations, and like say 100, every 100 operations, you must produce a new result, and this 100 bound must hold no matter what's the size of the input database. It can be extremely large, doesn't matter. You have a constant time guarantee. And so once you produce the first result, you store a state, and then you call the enumeration algorithm again with that state, and you must produce the next result, change the state, etc., until we reach a special state that says enumeration has concluded, and it must be the case, and then you have received all the answers to your query. Normally, many of you have seen this already. This is the context in which I'll be working, so for this enumeration problem. Now, knowledge compilation, again, he and Yujing's talks at the bootcamp have covered this. I'm not going to, I'm going to introduce d-DNNFs, of course, don't worry, but I want to tell you about this general approach to knowledge compilation, which we think is a great modular way to get enumeration results or other kinds of results. This is, at the left, you have the world without before knowledge compilation was invented. People would toil, like for each of these various problems represented with like 3 different colors, people would carefully design a specific enumeration algorithm for each problem. And we propose, with the knowledge compilation approach, each problem you will instead compile to a circuit. The idea of the drawing is that designing an enumeration algorithm is complicated because you need to understand things about both query evaluation and also the design of efficient enumeration algorithms, messy data structures, and so on. Here you have less gears, so it's supposed to be simpler. Just translate your query evaluation problem into a circuit in a specific class, and then completely forget about queries, databases, and so on. Just have a circuit. The class in which the circuit falls is the kind of invariant that's supposed to make your life easier afterwards. And then you just need one enumeration result saying on circuits of class blah, D, S, D, NNF, whatever, you can do efficient enumeration. And then these results are obtained by the product, combining these results with that result. At least that's the theory, but this is the approach that we wanted to investigate with this enumeration, knowledge compilation-based enumeration. Let me now present to you the circuit formalism that we use. Unfortunately, and this is the theory, in practice, in each paper, you end up introducing a circuit formalism that might be a bit different from what exists before, so it's like it doesn't plug in as nicely as you would want, but you will probably recognize these circuits as being related to the d-DNNFs you've been hearing so much about in previous talks, so hopefully this will not be too shocking. So these we call set circuits because they're not really Boolean circuits, but they are a concise way to represent sets of assignments. So let me define them to you. A set circuit is a DAG of vertices called gates. You have an output gate, which is where we're going to get the result of the circuit. We have variable gates, which don't have any input and stand for variables. Well, we have constant gates, true and false, basically. And then we have internal gates, product and union, okay? This is going to be Cartesian product. This is going to be set union. I will explain the semantics afterwards. But so people familiar with circuits might recognize them. People familiar with factorized databases might see this as a bit familiar. This is a kind of abstract version of a factorized database in some sense. What are the semantics? Each gate captures a set of assignments. So it's just a set of sets, but because set of sets is confusing, the inner sets, I will always call them assignments. So this is defined inductively. A variable gate captures one assignment, and the assignment captures what contains just that variable. Okay, just like a singleton assignment. The true gates capture one assignment, which is the empty assignment. The false gate do not capture any assignments. And the two combination gates, the product gates and the union gates. So the product gate is doing a kind of relational product or Cartesian product. It captures assignments in the following way. It's all the combinations of an assignment captured by the first input and an assignment captured by the second input. Let's say the product gates always have 2 inputs, or at most 2 inputs, so you get that. So in the example, you see here, empty assignment times singleton assignment x gives singleton assignment x. Singleton x times singleton y gives singleton one assignment xy. Yes?
Do we still think of the inner sets or assignments as tuples, or?
So the assignments, you could think of them as tuples, but they are really just sets. If you wanted to see them as tuples, you would want your variables not to be variables, but to be a pair of an attribute name and a domain element. Intuitively, X in a database setting, in a factorized database setting, these would be things saying column A contains value A. Well, column A contains value B, if that makes sense. But if you don't care about factorized basis tuples or whatever, this is just a complicated way to represent a set of sets. That's it. Union gates do the union of the captured sets of their inputs. Okay. So here, this circuit captures two assignments, x and xy. So if you're familiar with arithmetic circuits, you might recognize something that you like here, because I could see this as an arithmetic circuit by saying this is the constant 0, this is the constant 1, and this would be just the product of the captured polynomials, and this would be the sum of the captured polynomials, right? A set of sets, you can see it as a polynomial, so let me also reveal that people who like semirings might recognize something that they enjoy, the n of x semiring. You can see a set of sets here as a polynomial, like a monomial is a set, one without higher degrees than 1. A monomial would be just a set of variables, and a polynomial would be a sum of monomials, okay? So a set of sets of variables in some sense. And this then would correspond to sum, and this then would correspond to product. The task that we want to solve is enumerating the assignments captured by a gate, the output gate of the circuit in particular. So if, for instance, here we would want to enumerate first x, and then we would want to enumerate xy. Of course, if the assignments are large, we can spend linear time writing down the assignment, linear time in the size of that assignment, but no more. We're not going to work with arbitrary set circuits, but with restricted set circuits, so d-DNNF set circuits. Union gates must be deterministic, meaning the inputs are disjoint. No assignment is captured by two inputs, so this is taking a disjoint union of the input gates. And the times are decomposable, meaning no variable has a path to two different inputs. Times are taking the times of two subcircuits on disjoint sets of variables. So like in the inner union, when doing the relational product, you do not have duplicates, right? And what is the result then? So the result is that we can enumerate efficiently the satisfying assignments of circuits of this form. So given a d-DNNF set circuit, we can enumerate the captured assignments with linear time preprocessing and output linear delay, so delay linear in each assignment. We also have a part of this result, if you're only interested in results of assignments of a constant size, so for instance, you only want small assignments, or you're working with queries in data complexity and the size of assignments can be assumed to be constant, then the delay can be constant delay. Okay. Maybe you don't care like me about set circuits, and so you wonder, okay, this is very nice, but why do I care about d-DNNF set circuits? Where can you find these in the wild? Well, two possibilities. Either intentional query evaluation tasks. So you want to evaluate a query on a database and you will compile it into a d-DNNF set circuits. I will tell you later that this is possible. Or if you want to start with a Boolean circuit, you have a Boolean circuit, a d-DNNF in the usual sense of Boolean circuits. You can convert them actually to d-DNNF set circuits. It's just that d-DNNF set circuits are simpler to work with for the proofs. But if you have a regular Boolean d-DNNF, you can convert it. The only catch is that the conversion is not linear time in general. So if you have a d-DNNF that's without additional assumptions, converting it to d-DNNF set circuits might take quadratic time. Yes?
So it seems that they're really zero suppressed decision diagrams.
Exactly.
The variable is missing, it's assumed false. So
you have,
like ZDD would give you directly one of
yes,
those.
so you have correctly guessed what is the mismatch in the two semantics. Indeed, you can see these set circuits as a zero suppressed version of a diagram or of a circuit. And so the reason why we need to do this, the reason why the time is quadratic is because we need the d-DNNF to be smooth, which can take quadratic time to enforce. And once it is smooth, then the two semantics don't matter. But if it is not smooth, then indeed, the difference in semantics is that with normal Boolean circuits, when you don't talk about a variable, it means it can be true or false, it doesn't matter, right? Whereas with the set circuit, if I don't talk about the variable, then it's not in the answers. So it's basically implicitly assumed, implicitly enforced to be false. This is why we have this small problem. So if the d-DNNF is smooth, then you can do the conversion in linear time. If the d-DNNF is structured, you can do the conversion in linear time, not because we can really do smoothing, but because we can cheat. So because we can do implicit smoothing in linear time and get a d-DNNF set circuits, except it has some additional special gates standing for range of variables and for which enumeration also works. So I'm going to sweep this under the rug because I don't want to mess up my circuit formalism with this consideration. But remember that if you just work with Boolean, if you want to use this as I have Boolean circuits, I want to do enumeration, you want your Boolean circuits to be d-DNNFs and to be smooth. And if they are not smooth but structured, you can maybe enforce it nevertheless. Or you can pay quadratic time. And then you can do the enumeration. Right. So I will tell you a bit about how this result is proved, and then I will tell you about the applications. So the proof consists of two phases, the preprocessing phase and the enumeration phase. And the preprocessing phase is split into two steps. First, I will normalize the circuit to basically eliminate messy things that are going to make my life harder. And then I will index it with some, to make it easier to enumerate based on the normalized circuit. And then once we have the normalized circuit that has been indexed, we do this enumeration phase, delay linear in each result, and we produce the results. So I will explain to you what is inside these two boxes. But before that, I will explain to you what is inside that box, because I think it's easy to get an intuition of how enumeration works. So I'm going to give you a wrong version of this box that's easy to understand. And then I will fix it by explaining why we need to put things into these two boxes. So this is the easy but wrong story. How do we do enumeration for d-DNNF set circuits? Well, let's do an induction. Base case, I have a variable. I want to enumerate the satisfying assignments. Well, I enumerate the one assignment and I stop. Induction case, I have a union gate. How do? I want to enumerate the assignments captured by this gate. Well, I enumerate the captured assignments by recursing on the first input, and then I enumerate the satisfying assignments by recursing on the second input. If I have more inputs, then I recurse on all of the successive inputs, and I just produce the assignments for this one, and then this one, etc. Do I get duplicates? No, because it's a d-DNNF. So this union is disjoint, so each assignment is produced by one input. Times gate, let's do an inductive case too. Well, let's recurse into G, enumerate all the satisfying assignments, all of the captured assignments, sorry. And for each assignment, let's combine it with all of the assignments to the right. So we just do like two nested for loops. For each captured assignment of this gate, for each captured assignment of that gate, I'll put the concatenation. Does this pose problems of like a variable occurring both here and you get occurring twice when we do the concatenation? It does not, thanks to decomposability. No duplicate variables. The variables here and here are disjoint. Okay, so that concludes my talk. Not really. So I have swept some problems. So the first problem is handling the empty set. If you think of an arithmetic circuit, this is basically I have 0, and so some gates evaluate to 0, and I cannot waste time with them. Take this circuit, this set circuit here. This captures the empty set. When I do the product, it also captures the empty set. When I do the product, it also captures the empty set. And so it could be the case that large parts of my circuit are actually capturing the empty set because I'm just multiplying them with something that's empty. And if I spend time in this inductive proof here going down parts of the circuits that turn out to be empty, then this is messing up my delay guarantee. I do not want this to happen, right? Fortunately, I have linear time preprocessing. And in the linear time preprocessing, I can normalize to just get rid of these parts of the circuit that I'm not interested in. And this is, in fact, completely straightforward. Just compute bottom up for each gate, whether it captures something or not. It's completely trivial to do this in linear time. And then just get rid of the parts of the circuit that don't capture anything, so you will not be tempted to go into them. That's the normalization step. There is a second problem that we need to address in the normalization step, which is the case of the empty assignment. In arithmetic circuit terms, this is multiplying by 1. If you multiply by 1 too many times, then you can have big parts of the circuit that are just doing multiplications by 1 and not making any progress. So taking this, x times empty assignment gives you x, times empty assignment gives you x, gives you x, and so on. If you recurse into that gate and you need to go down all of this chain to finally get the variable x, then your delay is not going to be linear in the size of what you find at the bottom. You're going to waste too much time going down these things. So we have to simplify this stuff away as well. To do this, we do what's called homogenization meaning we split each gate between two copies, one gate which is only taking charge of the empty assignment, and the other gate which is taking charge of the non-empty assignments. And we change the wires to wire gates in the right way so that we can distinguish the empty and non-empty assignments. And then if you have times gate where one input captures only the empty assignment, you can just remove it because it doesn't have any effect. And now you're left with another problem, which is these times gates that have only one input. What I'm going to do with them? Well, then you can just collapse these chains, and basically, when preprocessing the circuit and going down times gate with only one input, you just connect the one input back to directly to the times gate, so that you ensure that you do not have times gate with only one input connected to another times gate with only one input. So once you have done, so you see, so this is not very complicated, it's just a bit tedious. Now we have normalized the circuit to get rid of these two problems, empty assignments and the empty set as an assignment. This is now guaranteeing that when traversing a times gate, we make progress. So this is a bit harder to visualize. If you think of the recursive algorithm, when you get into a times gate and the assignment, and when you get into a times gate, you're going to recurse now in two inputs of the times gate and combine the two assignments. And thanks to this preprocessing, you know that the assignments captured by the left and by the right are non-empty, right? They contain variables. So if you think about the big assignment you're going to produce in the end, it must come from something to the left and something to the right. And so the big assignment that you output has been split between the left and the right, meaning that when you produce an assignment with 42 variables, you can only have seen 41 times gate because each times gate has split the assignment that you were producing. So this guarantees that when producing an assignment, the number of times gates you have traversed is linear in the size of the assignment. So now each time you see a times gate, you're splitting the assignments being produced, so you're making progress, and so you're in good shape to get the output linear delay. Okay? Yes?
When you have that nested loop, right? So the inner loop is also guaranteed to not take too long because, so you have basically guaranteed that every sub-circuit is also giving you that same constant delay in its output size.
Yeah, I mean, when doing the recursive algorithm, I'm using inductively the fact that when I recurse on the two inputs, that they are producing each assignment in output linear delay in the size of that assignment, and so like combining them, I can get output linear delay. I have to spend, I mean, I need to concatenate them. I cannot spend linear time concatenating them, so I need like to output the first and then the second, because otherwise it would be quadratic. But yeah, it works. Okay. So we're good. Well, still have one problem. I don't know if you can see what the problem is. The problem is OR gates, union gates, and complicated structures of union gates. So I've told you when we see a times gate, we make progress. When we see a variable, of course, we're happy because this is easy. When we see an OR gate, union gate, we could be recursing and say, I won't produce the assignments captured by that gate. Okay, I recurse on that gate. I recurse on that gate and so on. And I could be spending lots of time going down in the circuit on union gates until I find something that will allow me to make progress. Yes?
So do you have a reason why all your gates have to have fan-in too?
So I can enforce it for the times gate. For the union gates, not. I could rewrite the circuit in linear time.
Associativity and commutativity of union, you could use union gates with multiple fan-in.
I could. It's easier, I think, to present the algorithm where the fan-in is 2, and like in the linear time preprocessing, I can change I can rewrite union gates so that they all have fan-in at most 2. But okay, and this is indeed using commutativity and associativity of the underlying semi-ring. I'm sure we can talk about if the semi-ring is different, and well, okay, no, a semi-ring should be associative. But
solve the problem that you have here.
I'm sorry?
Would that already solve the problem that you have here?
No, it would not, because even if the fan-in is at most 2, which is the case in this drawing, actually, I can still spend lots of time going down a chain of union gates.
I meant actually the other way around, using unbounded fan-in.
Even if the fan-in is unbounded, it could still be the case that all of the inputs are union gates as well, right? So what I could do is do a transitive closure, okay? And this works better indeed if the fan-in is unbounded, but the problem is I don't have, in linear time preprocessing, I don't have the time to compute this transitive closure, right? I really want my preprocessing to be linear. So to make this a bit more precise, when we get to a union gate, we want to get to a non-union gate as quickly as possible. So we think of all the non-union gates having a path to that union gate via union gates, and we want to explore these and enumerate these. We want to enumerate the union of the captured assignments by these gates, and we must find these efficiently. If I had enough time to compute the transitive closure, I could just connect all of these gates to the corresponding union gates. But since this is obviously not possible, and well, obviously it doesn't have linear size. I think, and conditionally, I'm not going to be able to do this in linear time, right? Yes.
Why can't you just collapse two nodes that are two union consecutive nodes?
I might be. I cannot always do this because I could have these two things could be feeding into different gates, and so I might even if this one feeds into this one, there might be some other gates taking the product of with this one and others taking the product with this one. So I cannot just collapse all of this anyways. I need to remember what has a path to which gate, but I cannot afford to compute the exact set. What I must compute instead is a structure allowing me to enumerate, given a union gate, what are the reachable exits. And this looks pretty challenging to do in a general DAG. But fortunately, we are saved by determinism. I had forgotten about determinism. Determinism also guarantees that you cannot have something like this, like a gate cannot have two different paths to the same union gate, because otherwise you would have duplicates. So if you think about a layer of union gates like this, it is not an arbitrary DAG. It is what's called a multi-tree. So do not confuse multi-trees with polytrees. This thing can still contain undirected cycles. A multi-tree is a DAG that does not contain a diamond, okay? And it so happens that we can find an algorithm to basically process multi-trees by pushing up at least one exit of a gate each time so that afterwards we can explore downwards in a way that will produce one exit each time we visit a gate. So this is not obvious. It's not very complicated. I can explain to you at the whiteboard if you want to ask me about it. But this can be done, and once this is done, it means the real algorithm is when you get to a union gate, you enumerate its exit with constant delay, and for each exit you recurse into it. Okay.
So yes. I think I missed something, but there is a linear bound on, regardless of the choice of exits you take, there is a upper bound that's linear that you will reach the exit, right, regardless of how you choose.
Yeah, but I want the outputs to be enumerated in output linear delay. Meaning if I'm producing an output of size 3, I must visit like some number of gates that depends on 3, not a linear number of gates in the circuit. So I cannot spend a linear time in the circuit to produce my assignment. And all of this is about finding a way to shortcut this so that each time, so what this ensures that when I get into a union gate, I can then, with constant delay, jump to a non-union gate, which would be either a variable or a times gate that splits the variables, and this is what gives me my output linear delay guarantee. Okay. Applications of this result. So I have motivated all of this with intentional query evaluation, but where I lie is, of course, I don't do query evaluation in the usual database sense. In the usual database sense, I meant monadic second-order queries, of course, over trees, which are special kinds of database. So we have a tree. The database is actually a tree with nodes colored from an alphabet of possible colors. My query is written in this very practical language of monadic second-order logic, which generalizes CQs, UCQs, first-order logic, and allows quantification over sets. You can talk about reachability, descendants in the tree, whatever. So for instance, this is an uninteresting MSO query saying, find me all of the pairs of the pink node and the blue node. And I want to enumerate the results of such queries on trees. So find me all pairs of nodes of the tree such that this query holds. And I'm measuring data complexity, so the query is fixed. Just measuring efficiency as a function of the input tree. I'm hiding a non-elementary dependency in the query, of course, when I do that, as usual with MSO, but this is theory. And if you don't like the non-elementary dependency in the MSO query, I will be talking about efficient combined evaluation data. It was known before us, that proved by Bagan and by Casana and Segou, found that we can enumerate the answers to MSO queries on trees with linear preprocessing and constant delay. So thanks to the circuit result, we can provide an alternative proof of this fact. So given an automaton representing the MSO query, okay, well, we can prove this via this intermediate result saying, if I have the MSO query expressed as a bottom-up deterministic tree automaton and I have the input tree, by doing a kind of product construction, I can compute a d-DNNF set circuit capturing the results I'm interested in. This is the compilation result. And then you just invoke the enumeration algorithm I presented to you, and you get this. So this equals this times the previous result. Yes?
What will be the size of this circuit?
It will be the same size that it takes to produce it, so automaton times which is, yeah. So the non-elementary dependency in the query is hidden in the fact that this A is very large as a function of the MSO query. This is where the problem is. If you start by giving me a small automaton, then there is no catch. This is a result in combined complexity, actually. The circuit approach allows us also to study efficient update support or incremental maintenance. We also have talks about this in the program. We can support relabeling updates to the tree, meaning if the tree is changed and some node colors are modified, we can handle these in logarithmic time and update our enumeration structure without having to rerun the entire linear time preprocessing. So this task of enumeration plus updates had been studied before, and this was a new result that we can get thanks to circuits. And circuits are a nice thing for incremental computation because it's easy to see when you have a circuit and I have a gate, I can condition to change this gate to be something else. Okay. So, and all circuit computations are bottom up, so all of this lends itself pretty well to update support. We have also claimed in 2019 that the same was true for updates to the trees of the form inserting a leaf, deleting a leaf. And unfortunately, there's a broken dependency problem with this result, because this result depends on another result that turned out to have an erroneous proof. There is a revised version of that proof currently under review, so hopefully we'll soon be able to replug a correct proof of the auxiliary result and get back the... so this is like co-inductive result proving. So far what I can tell you is a conditional type result saying, assuming there exists an algorithm with that specification, then we get that. Application 2, document spanners. So this is the context where I want to do information extraction. I have data which is text, and to a theoretician's mind, text is just a special case of a tree, although many people wouldn't see it that way. I have a query which is a regular expression. Again, the theoretician doesn't see the difference between a regular expression and a monadic second-order query. You can sell the same result with a completely different disguise to a different community that way. And what you want to get is which substrings match the pattern. So this means think that you're crawling the web, you have lots of text, and you want to find anything that looks like an email address. So a word surrounded by two spaces and containing an @ sign. And you want to output efficiently the list of all of the email addresses you have found on the web. Because say you want to warn all of these people that they could get scammed or phished by bad people because their email address is available on the internet. Let's imagine. The goal is to be very, very efficient in the text, so constant delay enumeration of that stuff. What's new? So this is not just a repackaging of the previous result, because now I want to also be efficient in the pattern, so have polynomial time data complexity. So this is not an MSO formula. This is a regular expression, which is something that I am told people actually use out there in the real world. I want to be polynomial in that regular expression. I do not want to be exponential or worse. And we can show that this is possible because we can enumerate the results captured by a non-deterministic automaton with captures, which is a weird automaton formalism that you can get in p-time from a regular expression with captures. And the preprocessing is linear in the text and polynomial in that automaton, and the delay is constant in the text and polynomial in the automaton. This is also showed using some kind of product construction between the automaton and the text, and then applying enumeration. And it generalizes an earlier result where, so this had been known before for deterministic automata, But if you're given a regular expression, you cannot efficiently convert it to a deterministic automaton. So you really need the power of this to work with non-deterministic automata, which is nice because it's a technically challenging question, but it works. I would be lying to you if I pretended that this is done via a nice knowledge compilation approach. You could phrase that proof as in a circuit-based thing using bounded width UOBDDs. And it generalizes to trees, and then it would be using bounded width sets D as d-DNNFs or something. It's not, well, for the document spanner result is not written in this fashion, but conceptually this is what's going on. And yeah, we can do the same thing on trees. So on the thing is, on trees, you don't really have a language for regexps. So it doesn't really make so much sense to talk about being tractable in a representation of the automaton because it's not really clear what the representation should be. But there's no obstacle to doing that. Application 3, very quickly, we have been working on generalizing beyond MSO and automata to work with annotated grammars. So you have text, which is now, say, source code in some programming language. You have a pattern expressed as a context-free grammar with terminals. And yeah, we want to find all quoted strings in the program, for instance. And then we can also do enumeration to find all occurrences of a pattern like this. If the grammar is unambiguous, which is necessary to get a d-DNNF, kinda. And the preprocessing is no longer linear in the input word, but it's cubic. And we have, well, subclasses where the preprocessing can be made quadratic or linear up to assumptions in the grammar. So this improves on an earlier result that had a worse bound on the preprocessing and a slightly different model of grammars. I think it's time for me to conclude, despite all of the earthquake shenanigans. So there are other applications to these kind of techniques using circuits for enumerations. So Martin Munoz and Christian Riveros in Chile are also using this. So they don't call it d-DNNF set circuits. They call it enumerable compact sets. This is a marketing difference. They see it as not really building a circuit, but constructing a kind of data structure that's fully persistent by adding gates to a circuit. So this is a difference in vision, but it's really technically the same thing that's going on. And they have enumeration results using these enumerable compact sets for visibly push-down transducers on nested documents and for automata on SLP compressed documents. There are also results for query evaluation. So you might say, I have lied to you because I've said query evaluation, and then it turned out only to be about this MSO stuff. Well, if you want to evaluate first-order queries, not MSO queries, on bounded expansion databases, there is a result by Toronchik that uses this set, the set circuits terminology to get enumeration for free, kinda. And if you want to do CQs on and use these results, you can also do it. And Florent will be talking about this this afternoon. And there's also a recent paper by Berkholz and Vinal Smith about enumerating homomorphisms between structures that uses something called D-representations, which is pretty related to these circuits, and uses it to get enumeration results for enumerating homomorphisms between structures. One word about ranked enumeration. There is a big problem with enumeration algorithms is that there is no guarantee in which order they produce the results, which I think for practice is not great. We motivate enumeration by saying, oh, you can get the first results quickly and then you can ask for more results. But if the results are provided to you in a random order, that's not very useful. Think about a search engine that would just return all of the pages that match in an arbitrary order. It wouldn't be good. So for MSO, which is the main thing I do, the ranked enumeration is possible with logarithmic delay. It had been shown by Pierre Bourris and others, and our recent work is about extending this to MSO on trees. The very high-level idea for the recursive algorithms with products and unions is that you will use priority queues in the middle of the algorithm. And there are also works for ranked access, which is which is stronger than ranked enumeration, for conjunctive queries, including by many people in this program. I think Florent will talk about this as well in the CQ context. So to conclude, I have presented to you how to enumerate satisfying assignments of d-DNNF set circuits with linear preprocessing, output linear delay. I have shown you how to apply this to intentional query evaluation for MSO on words and on trees, and also some other applications, and other things like incremental maintenance, ranked enumeration. What's next? from most immediate to least immediate. I'm here for the rest of the program. I'm happy to talk to you about details of any of these things or discussing research about these questions. What about negation gates? There are no negation gates, but if you want to do enumeration and you get negation and you want to remove stuff, it seems to mess up enumeration and we don't really understand what could be done. Is determinism really necessary? It's of course very useful, but I don't think we know of lower bound saying you wouldn't be able to enumerate if you hadn't determinism. What about updates? So handling updates to the data with better than log n time, knowing that in some cases when you want to do incremental maintenance of these things without enumeration, you can get down to constant time updates or log n time updates. What about enumeration with better than output linear delay? And we have with Michael, we have a funny model of enumeration by editing previous answers in which it would make sense to look at this question. What about connections between automata classes and circuit classes? This is something that I think other people in the program are interested in as well. And yeah, can we follow this intentional approach to classify enumeration tasks by looking at the circuit classes to which we can compile them and try to get a better understanding of existing enumeration results using this knowledge compilation-based framework. That's all I wanted to say.
Questions?
Can you uniform the sample with linear time?
Not necessarily. If you can do counting, then yes. So of course, if you can do counting, then you can use this for uniform sampling. And if the circuit is deterministic, then you can do it. But it's not related really to the enumeration results because the enumeration results also work without determinism in some cases. And so what I want to say is we have the classes of circuits that are non-deterministic on which we know how to enumerate. So, and we know that we probably cannot count. So I would guess that this means there are classes where you can enumerate, but we don't know how to do uniform sampling.
Because otherwise you can just repeatedly call a uniform sampler and then with very low probability you'll get collisions.
At the beginning, yes, but as you go on in the enumeration, you're going to have more and more collisions, no?
Is the correct also you're expecting?
Yeah. Yeah, like a polylog delay, I think.
Yeah, okay. So I haven't done anything like this. I don't know if people have tried to do enumeration the way you suggest.
So yes, we did with Jan.
Okay.
We have a paper like this with Jan Strozeki, where we exactly do that and use column corrector to basically bound the time, and we use like hyperlog to maintain small footprint and remove duplicates with hyperlog.
Okay.
Yeah, I'm still trying to understand how you go from a database to a circuit. So say I have a table with 2 rows and 2 columns. Mm-hmm. So is that just a union node, and then on each side you have 2 product nodes?
So you can see this as if your data is like this, you can write it as what you suggested, yes.
I see.
This is like the DNF version of the data. But if the data is like this, then you could factor and you could write it like in a factorized database way, like this. See?
Okay, thank you. Yeah.
Some quick question? No? Okay, so let's take the speaker again.